Okay, hello. My name is Daniel Sussman, and in this series of short videos, we're going to be thinking about non-metric interaction rules in models of active matter. Right? And the perspective that we're going to be taking here is that, in the last week or so, we've learned a lot about performing agent-based simulations of a lot of physical systems, right? We learned about the basics of performing molecular dynamics simulations. We learned some fun tips and tricks and some advanced techniques. We learned how to use some existing software packages to do these things. And in this next little bit, let's think about how when we start studying active matter, right, and we start thinking about, the range of soft, squishy, out of equilibrium, complex systems that come up in the study of soft matter systems, we're going to think about what generalizations to some of the simulation techniques we need to think about, and what kind of physics those generalizations correspond to. Right? So, to a certain extent, this is going to be a little bit of a different perspective, where we're going to think about this first from the perspective of algorithms, and then we'll think about what those algorithms have to say about physical systems. Right? So, to start out, let's think about what I might call, algorithm 1, which is really just the fundamental loop that underlies all molecular dynamics simulations, right? At heart, what all molecular dynamics simulations are doing are basically the following steps. Step 1, you initialize your system in some way. I'll call just the set of variables of that system capital X, because who cares? This might include all positions. It might include all, velocities of some collection of interacting units, right? Maybe it's a bunch of soft spheres. Maybe it's a bunch of Lennard-Jones units. Maybe it's a collection of active, out of equilibrium, rods. Who knows? In any event, you do some steps to initialize your system according to some protocol, and then basically you run the following loop for as long as you're interested in. So for, some number of time steps. For some number of time steps, what you do is you say, well, first, evaluate all forces. Think about all the set of interactions that exist between whatever degrees of freedom you're defining. So you somehow evaluate all of your forces, and then, part B of this loop is something like update the state of the system based on the set of forces, right? And the details of, this step can vary a lot, right? You could be doing strictly equilibrium simulations, and maybe you're just working, saying explicitly forward integrate Newton's equations of motion, and then, that's the set of rules you have. And maybe you use velocity Verlet, maybe you use a leapfrog algorithm, maybe you work in a different ensemble, so you add, a thermostat of some sort to put you in the, constant temperature ensemble, or you add a barostat to be in a constant pressure ensemble, or something like this, right? There's many details here. They're all important, but for the purposes of this section, I'm actually not going to think too much about what those details are. Instead, what I want to focus on is this step where we say, well, let's think about evaluating the set of forces, right? And, a common situation that we find ourselves in, a common situation might be something like forces are all pairwise. Are all pairwise, and they come from some potential. So that, say, the force on degree of freedom I is given by some negative gradient of an energy with respect to moving the ith degree of freedom, right? So often we think about pairwise forces. Sometimes we think about forces that are, 3 or 4 body, especially if you have angular potentials or torsional potentials. But for the time being, let's just think about these kind of pairwise force situations. So this is a common place we find ourselves in, and the naive way to evaluate a complete set of pairwise forces among n degrees of freedom, the naive way of evaluating that would involve of order n squared mathematical operations, right? That is to say, you might have to do something like for I in something like 1 to n, and then for j in 1 to n, compute the distance, Ri minus Rj, respecting periodic boundary conditions and doing whatever you do, and then you say, perhaps if this distance is less than some threshold, if you're doing, say, Lennard-Jones interactions with a truncated potential or something like this, or soft spheres with an explicitly finite range of interactions, if the distance is less than some threshold, then I and j interact. Right. This is kind of the most obvious way to, loop through all potential pairs of degrees of freedom in your system and check if you need to include an evaluation of the forces for any particular pair. Here I probably said for j equals I plus 1 to n. That's kind of a detail, right? And, the rest of a molecular dynamics simulation is typically, more like of order n or n log n, depending on the type of simulation you're doing. And so having this operation that requires us to do n squared, of order n squared operations is not, well, it doesn't make us happy. And so, this is a major point of optimization, right? And so in one of the earlier lectures, we learned about things like, cell lists and Verlet lists and similar kind of acceleration structures that let us, for finite range potentials, find all pairs of interacting particles, not in order n squared, but something like, order n log n, right? Something that's really much more computationally tractable while still maintaining a very kind of parallelizable structure to all of the algorithms, which is something that's, of course, quite important in modern computation, since more and more of our hardware is moving towards, distributed computation across many CPU cores or GPU cores or tensor cores or what have you, right? So this using these kinds of optimizations makes us think about kind of modifying the fundamental molecular dynamics loop to be a little bit more general, right? So we still, step 1, initialize the system, and then, for a bunch of time steps, we're still gonna kind of repeat this loop over and over again as we evolve our system. Maybe we collect statistics along the way, or we do some calculations, but fundamentally, we're looping over a bunch of time steps. And now we might do something like, find all neighbors. And then just evaluate forces between neighbors, right? And what I mean by neighbors are things that would interact according to whatever force law we're interested in simulating. Evaluate forces between neighbors, and then, based on those forces, update the state of the system, right? And going through this loop is how you end up with, very nice simulations of things like this. I just went ahead and Googled molecular dynamics video, and, you get things like this. Right? So you can simulate simple models of water, or xenon, or colloids, or whatever you like, right? And that's great.